In this video, we're going to focus on solving exponential equations of type 1. Type 1 equations are the ones where both sides either have the same base or they can be written with the same base. Let's look at some examples. We need to remember one-on-one property for exponential functions. So if a to the power u is equal to a to the power v, then u and v are equal. That means if two output values are equal, then two input values are also equal. So here's first example, and we need to solve this equation. We have 5 to the power x minus 4 equals 1 over 5. So we can write it as 5 to the power x over x minus 4 equals 5 to the power negative 1. My goal is to write both sides with the same base. So now bases are same, my output values are same. That means the inputs have to be equal each other. So if the bases are same, the exponents have to be same as well because these two outputs are equal. Now keep in mind, we're not canceling the bases, okay? Some students will cancel the base. That's not what we're doing here, and that's not the correct way to think about it. We are using the one-to-one property. That means if your output values are equal, then input values are also equal. If the base, as long as the bases are same and the output values are equal, the exponents have to be equal to each other. So let's go ahead and solve it. Add 4 to both sides. 4 minus 1 is 3. So x equals 3 is the solution here. Another example, 2 raised to the power x plus 1 equals 16. Well, it doesn't look like they have the same base, but we can write both sides with the same bases. 2 raised to the power x plus 1 equals 2 to the power 4. Now again, using one-to-one property, that means my exponents also have to equal each other. 4 minus 1. Again, I got x equals 3. The next example, it looks like a little bit more work here. Example number 3, because I do have things going on in the numerator and denominator. So let me go ahead and write this. I'm going to try to write everything with the same base on both sides. So here, what's going to happen between these two exponents? They are 3 to the second power to the power x. These two exponents are going to multiply to each other, right? So 3 to the power x squared over 3 to the power 2x equals 3 to the power 3. Now, I can use the property of quotient rule of exponents. I do have the same bases, different exponents. I can subtract the exponents. So this becomes x squared minus 2x equals 3 to the third power. Now using one-to-one property, I can equate the exponents. X squared minus 2x equals 3. X squared minus 2x minus 3 equal to 0. X minus 3, x plus 1 equal to 0. So I got two answers in this case, positive 3 and negative 1, and they both are okay. So for example number 3, I got two answers. Both of these answers will make the left side of the equation and the right side of the equation equal to each other. Okay, next we got example number 4. Let's go ahead and look at example number 4. 7 to the power 3x, I can write 49 as 7 squared to the power 4. 7 to the power 3x equals, these two exponents will multiply with each other. So 4 times 2 is 8. Now using one-to-one property, I can say 3x equals 8, and x comes out to be 8 divided by 3. And that's my answer here. You can always plug the x back into original equation to check and make sure you got it correct. You're not required to. If you're confident about your work, that step can be missed, but I always prefer double checking my work, making sure that I haven't made a mistake. Let's look at example number 5. 8 to the power x plus 3 equals 2 raised to the power x minus 1. Okay, so 2 to the third power is 8. And I do have 2 to the power x minus 1 here. Now what's going to happen between these exponents? They're going to multiply. Very important. This is the step a lot of students miss. They forget to distribute the 3 into entire outer exponent. So the 3 is going to multiply with the whole outer exponent, not just with the x. Okay. So 2 raised to the power 3x plus 9 equals 2 raised to the power x minus 1. Now we can use one-to-one property. And one-to-one property says that If the outputs are equal, the inputs are going to be equal. We can say 3x plus 9 is equal to x minus 1. Subtract x from both sides. We are trying to isolate the x, so this will give me 2x equals negative 10. X comes out to be negative 5, and that's my final answer in this case. Again, feel free to plug it in, check and make sure the left side turns out equal to right side. I'm just skipping checking work, saving time here, but I do recommend that you check your work to make sure for your own peace of mind. So 2 to the power 2x equals 8 can be written as 2 to the third power x minus 1. Again, these two exponents are going to multiply. So 2 raised to the power 2x equals 2 to the power 3x minus 3. Using 1-to-1 property, we can say the exponent 2x is equal to 3x minus 3. Let's go ahead and isolate, solve for x, subtract 2x from both sides. X equals 3 is what I'm left with. All right, another example here. The nice thing, my base is already same. 2 raised to the power 3x plus 5 equals 2 raised to the power x squared plus 1. I can just go ahead and make the exponents equal to each other. Now it's a quadratic equation. To solve it, I must bring everything to one side, and x minus 4, x plus 1 are the factors. So 4 and negative 1 are my two solutions for this equation. One more, 4 to the power 3x minus 7 equals 32 to the power 2x. Again, your goal is to write both sides with the same base if possible. Sometimes it's not possible for an exponential equation. For example, 7 to the power x equals 10. You cannot write both sides with the same base. This will be a type 2 equation. We will discuss them a little later when we have talked about logarithms. But for now, we only focused on the equations where we can write both sides with the same base. So I cannot write 32 as 4 raised to some power, but I can express both sides as 4 can be written as 2 squared to the power 3x minus 7. 32 can be written as 2 to the fifth power to the power raised to the power 2x. So these two exponents are going to multiply now. 2 raised to the power 6x minus 14 equals, these two exponents are also going to multiply 10x. Now, using 1-to-1 property, we can go ahead and use 1-to-1 property now. 6x minus 14 is equal to 10x, and I would subtract 6x from both sides. Negative 14 is equal to negative 4x. 14 divided by 4 is x, which gives me x is 7 over 2. 7.5 or 3.5, however you want to input your answer. Let's look at number 9. Again, my goal is to write both sides with the same base. Looks like I can write both sides with a base 3 here. Let's go ahead and give it a try. First of all, 9 to the power 2x plus 1, 27 to the power 1/2. Now I'm going to write both sides with the same base. The base would be 3 here. 9 can be written as 3 squared. And 27 can be written as 3 to the third power to the 1/2. So these two exponents are going to multiply with each other. 3 raised to the power 4x plus 2 equals 3 raised to the power 3/2. Now using 1-to-1 property, we can say because the output values are equal, the exponents have to be equal. 4x comes out to be 3/2 minus 2. 3/2 minus 2 will be negative halves. Once you make the denominator same, that would be 3 minus 4, which is negative 1. 4x equals negative halves. X turns out to be negative 1/2 times 1/4, which is negative 1/8. And that's our end product for this equation, and that's going to be our solution. X equals negative 1/8. Okay, now x is the exponent, okay? The exponent can be negative, so don't worry too much if you get a negative exponent. There's nothing wrong with, there's no domain restrictions, nothing wrong with having a negative exponent, okay? That's all for solving exponential equations of type 1, where both sides either already have the same base or they can be written with the same base.